Hello YouTube, let's take another look at this Crafting Interpreters book. So in the last episode we finished the scanning chapter. So we have a scanner class that can now read strings like this and produce a sequence of tokens that represent this. But what we are getting to now is trying to turn these tokens into some kind of representation that can be executed by our interpreter, which we are soon to write. So I read a little bit of this chapter. I recommend you give it a look, but I won't go over it in super detail. But basically we want to turn this text first into a series of tokens and then into a tree representation like this that kind of indicates how you should execute it. So there's a lot of things about different types of grammars, and the basic way it works can kind of be seen here. So this is a grammar for breakfasts, and it has different types of characters. So the quoted ones are so-called terminals. They cannot be expanded to anything, and the non-quoted ones are non-terminals and they can be expanded. So what does expanding mean? Well, let's take a protein with breakfast on the side. So protein is a non-terminal, so it can be replaced by one of the rules for protein down here. So for example, we can put in crispiness, crispy bacon. So you see that we kind of just did a replacement like this, and now we can do another replacement where this time, let's say we want to replace crispiness, and it can be either really or really crispiness. So we just replace it with really. But another thing we could do is do this, which is also valid. And then finally, let's replace breakfast with bread and bread with toast. So that kind of gives you an idea of how these diagrams, or whatever you want to call them, these grammar rules should be read, as replacement rules with things that can be replaced, things that cannot be replaced. And he also has an example here that you can look at. And we're trying to write this language logs. So to do that, we need to, the way you normally do it is you define a type of grammar like this, but for the things that can appear in your programming language. So it's apparently quite large. And in the previous chapter, we did the entire lexical grammar in one fell swoop. But to do the syntactic grammar, which is this kind of replacement thing that I was talking about, it's larger, and we won't do the whole grammar before we write the interpreter, he writes. So we'll start with a small subset that, and then we can get the interpreter up and running. So for example, we just want to pass simple expressions like this, is 1 minus 6 less than 4. So this thing. Now to do that, here is the syntactical grammar we'll use. So the base case, you can say, or the most general thing you can have is an expression, which can be literal. Okay, so maybe I should say that he defined a different way to write it. So you can see here, we wrote breakfast. It can turn into protein with breakfast, or it can just turn into protein, or it can turn into bread. But to show different options, he has this notation of a line. So bread, instead of writing bread to toast, bread to biscuits, bread to English muffin, you can just write bread to toast, or you should read it as or biscuits or English muffin. And here protein, for example, it can be, now there's like a grouping with parentheses. It can be, it always has eggs, but then it can be scrambled poached or fried. And you also have these like regex things that you can have 0 or 1 character, 0 of 1 times this string. So crispiness is really, and then 0 or infinitely many times really. Another way to write that is with the plus operator, which you may know from regular expressions, which means it's either 1 or infinitely many times, and then there's the question mark, which is 0 or 1 time. So anyway, so let's look at this grammar now. So we have the expression, the kind of the basic thing, can be a literal or a unary or a binary or a grouping. And a literal is simply a number, a string, or it's these like constant strings, you can say. The reason that we write number and string like this is because a number can obviously be 1, 2, 3, it can be 1, it can be, you know, something like this. So the length of it can vary a lot. It's not a constant thing. And a string, again, it can also be multiple things. It's not a constant, but true, for example, or false or nil, those are constant strings. Now, then there's the grouping, which is just an expression inside of parentheses. Then there's a unary operator, which is either we support minus or we support the logical not onto an expression. There's a binary operator, which is expression, operator, expression. So just like 2 times 3. So if you want to like try to, and then there's the operator, which is equals, equals, all of these like standard operators. So for example, we could try to pass this sub thing. Or we could like write how it would be written. So it's a binary operation. So we can start by just thinking of it like this. I'm not sure what exactly I'm trying to say here, but, and then the expressions, I don't know. So let's say it's a binary operation, which means that it's the same as expression, operator, expression. And to make it fit or whatever, it's clear that the operator is the multiplication, and what's it called? The expression is a number. So I'm not really sure what I tried to show you with this. I hope it makes some kind of sense. But basically you can also say, let's start with an expression. Let's substitute it for a binary, which is equal to expression, operator, expression. And then we can substitute expression for a literal. And then we can substitute literal for number. And then we can substitute up for multiplication. So this is how you would generate something matching this. But anyway, let's keep going. So now we want to make some kind of expression for these things. Let's say, we want to make a code representation of these literals, unaries, binaries, groupings, so on. And the way he wants to do it, because he's working in Java, is to instead of making a single expression class with an arbitrary list of children, he wants to make a base class for expression and then extend it. So let's have a look how that looks. I'm not really sure exactly how Java works, but you define apparently an abstract class expert here, and then different subclasses extend it, they inherit from it, whatever, and you define some fields on there, and then later on he will presumably write a function to take in just an expert and then do things with it. But we can, let me just see something. Okay, so he calls it generate AST. So let's also make a file called that. Just for good measure, let's add it here. And we don't want this something gross. We don't really have base classes, inheritance, or anything like that. So we will make instead an enum, which we call expert, and it can have a variant binary, which will have a this is how we would like to do it. As an expert, it has a token, an operator, which is evidently a token, and then has a write thing, which is also an expert. And then we want to say use create scanner token. Let me just check here. Should it be token type? I'm not sure why it should be token, because it has all sorts of information that you don't need. But okay, let's keep it like that. Now, if we try to compile this, it will give us an error where it says that you cannot. It says recursion without indirection, and it's because the compiler cannot know the size of this thing at compile time. So you need some indirection. So we box them, which is basically the same as taking a pointer, as far as I can understand. So we instead of just an expert, we say we have a pointer to something, and that should be good. Okay, let me read a little bit more and then I will get back to you. Okay, so apparently I was a little bit confused about what he was doing. So later on he says that this is a lot of code to write. I mean, for us it's quite simple, but what he wants to do is write a script to generate all this stuff. So that's like not something we need, in my opinion. So what I want to do is just to rename this thing into expert, which is what he calls it later. And then let's go into main and just call this expert. And finally reopen it. Okay, so now it's called expert RS instead. And let's see what the next thing is. Right, so he's running this script, but we don't have a script, so we need to actually write these things. So let's do that. So we want a grouping, which should have just an expression inside it. And then we need a literal, which he says, is an object. So it's a value, but what was the... It could be a lot of things. So I wonder if what would make sense here? Would it make sense to define another enum, literal value? I think we did this before. So it can either be a number, string, and we'll put like also a value in here, and it's a little bit annoying, that's called string, so let's call it str, and it will contain a string value. That's surely going to be confusing. Then it could be true, it could be false, and it could be nil. So don't we already have these? Yeah, we have a lot, but they are not all valid literals. So I don't know, string value, called it before. Let's just go with this thing for now. It seems a little bit weird, but whatever. So he also wants to generate the unary thing, which will have an operator, token, and a right expression. And now we should be good to go. So a bunch of warnings that I still haven't removed, but that's fine. Now let's see what happens next. Okay, so basically now he's talking about how to work with trees or whatever, you know, how to interpret these values. Like say we have an expression, how do we actually execute it? And basically all of this is saying that the best thing you could do would be to pattern match, but since you can't do that in Java, he has to use the visitor pattern. So I won't really think too much about this because we have pattern matching in Rust, so we can just do the easy thing. And now he's also talking about generating these methods for the visitor. So we'll kind of skip this one, I think. Before we end this round, simply see the pattern in action. So I think actually we don't have too much to do in this chapter. So let me just read the last bit and see what we can get out of this. Okay, so I don't really care about this code because our code is going to be very different, but we want to make a pretty printer, which basically, you know, takes this stuff here and turns it into something where we can see what the actual structure was. And he's producing this Lisp-like representation, which is fine. I think we will do the same. So we can write it as a kind of a method or whatever you want to call it on the expa. We'll call it we'll just call it print, and it will take a reference to self and return a string. And maybe it shouldn't be called print then, maybe it should be called, you know what, it will write to output. It will actually also print it. So maybe let's just, for completeness, let's define a toString. And also a print, which won't do anything. It will just print whatever comes out of toString. Because I feel like we would often want to just use this interface, but sometimes maybe I want the string. Okay. So basically, we just want to like match on the different cases and do something that makes sense. So I'm just writing all these to-dos because I just want to verify that this actually compiles. And it did not, because, you know what, let me just add this. And now we just have some warnings. So for example, okay, I just formatted it, it changed it quite a bit, but whatever. So for example, if we have a, let's take the unary operator first because it is the most, well, I don't know. But we want to return a string. So let's say the string we want should look something like this. It should have so we want these parentheses, so it's kind of like Lisp, which just encapsulate this single expression. Then we want the operator to string, and we want, so we can write it like this, operator string, write string. Hope this makes sense. We haven't defined those variables yet, of course, but, and then we just actually return this. So we can just say the result is this thing. Right, but what is operator string? So operator is a token, and I don't think we had like a token to string. Actually we did, but I don't want this implementation. I just want, I think I just want this. Let's just take the lexeme actually. It's kind of weird, but right, so write string. Let me see what he did actually. So if you visit the unary, yeah, he just takes the lexeme as well. So, okay. So the write string is a pointer to an expression. So can we do this? And then just for quick test. No, it didn't like that. How, I never remember how you're supposed to read it. Okay, so is it like that? Oops. Okay, whatever it is, doesn't matter. So we need to access these now, so I'm just gonna make them public. Don't hate me. So now it should only be warnings, it's only warnings. And then we want to take whatever is inside this thing and turn it into a string. So how do we do that? We probably dereference it, and then we call to string. So we kind of recursively call this function. Now it should compile. And it does compile. So let's see, what should we do with the value? So the value is a literal value, and I kind of just want to implement a toString on this thing. And how is it? Is it like this? If it's a string value, then we just clone the string. If it's true, we write true. If it's false, we write false. If it's nil, we write nil. So should be okay. It's not because of this. So funny you cannot refer to the same, like the enum inside the implementation of the enum, but maybe there's a way, just not aware of it. Yeah, right. So these guys have to go to string as well. All right. So now we can simply say that we want, again, a parentheses and then something inside it. And the thing inside it is value to string. And the grouping, what do we want to do with the grouping? He wants to do like this. Which, let me just check that we get the same for value actually. I think so. Okay. So, same thing, but now we write group, and then whatever is inside the group should be toStringed, so expression to string. And cannot format that right now because something is wrong. There we go. Okay. Now finally, this one should be very Lisp-like. So the operator to string, the left to string, the right to string. Now the question is, the operator, what type was that? It was a token. So instead of toString, probably we call lexeme again. And it's funny it didn't complain before. I wonder why that is. It's very interesting. Ah, no, it does complain down here. But it's a string, right? So we can clone it. And that is fine. So this should pretty print things. Let's actually try to use it. So ready print an AST. So let's first make an AST, which could be a, let's say, why don't we do this expression? So it should be a binary where the left is a unary on with the operator. So we need like minus token is like a token. And now we have to see how that is defined. It's a little bit, is there like just one called minus? Yes, so it should be minus, minus. We can just put none and we can put -1. And it should have a it should have a, like a 1, 2, 3. So it should have 1, 2, 3. Another expression which is a literal, which is just a number with value 1, 2, 3. And that should do so we can put that in here now. So minus token and 1, 2, 3. And the operator is I think it's called star. The operator is the multiplication operator, and the right side is a grouping on just a literal, which is a number of value 45.67. Then we put that group there, and then just for now, let's print it and run that. So, of course, it didn't compile. So I see the problem. No, the lexeme is a string, so we just have to call toString. toString. That should expected identifier. Okay. So we really have to say token type lexeme. Okay, there's another problem. So weird. Sure, I'm doing something very silly. But okay, so we have a grouping, which has an expression, which is a literal, which has a value, and then we have a token, which has a token type. It's going to turn out that it's something else entirely and not this thing. Going to be sad. Okay, at least I can format it. I cannot run the test, so token type. And now I'm just gonna use the whatever they were called. Use super literal expr. Right, so we cannot have -1 because it's a U size, so. Okay, now a real problem, so we gotta box these things. Fair enough. And the left again has to box something. And everything has to be boxed. Oh, the token doesn't have to be boxed, but the expression does have to be boxed. Operator again doesn't have to be boxed, but the group has to be boxed. Not the nicest thing you could want. Error while passing the structs. what is the error? I don't see the problem at all. So unary. Yay, it ran. And here is the output. So we also have these extra parentheses compared to his implementation, which we can easily remove by saying that the literal doesn't get parentheses. And now we're good to go. Okay, it's really annoying to make these things. I wonder if there is a way to automatically convert things into a box. Boxes, maybe box is kind of like a reference. So what if we do like this? No, it doesn't like that. So maybe that is topic for another episode, but at least for now we got started on the expressions, which is very simple right now. It's binary, grouping, literal, unary, and we saw how to operate on this. So right now we only have toString, but later on we will like have a function that's called interpret or whatever, which will actually take a string like this and not just print it, but actually evaluate it and execute it. So the final thing we should do is check that the result is correct, so we don't have to like manually inspect every time. So result should be equal to this thing. Come on, Emacs. Run it. It fails. It fails because I add an extra parent. Wait, what? Okay, it fails because we are missing a parenthesis somewhere. We are missing one here. Amazing. So it was actually useful to make this test. So we look here, now it's okay. Okay, that's it for this time. See you next time.